Thank you very much for the invitation to the series, and thank you very much to Jonas and Michele for giving such a detailed introduction to the area. So I will report about some very recent activity at Santorini and about some data which we've acquired very recently. So this is an image of Maria Esmerian, and it was taken in December 2024, so just shortly before the crisis. Okay, so during the last decades, terrestrial volcanology made tremendous progress in forecasting volcanic eruptions. And this is mainly due to the availability of new remote sensing applications like INSA, but also by the possibility to analyze data streams, for example, from seismic networks in real time. Unfortunately, these achievements are only very hard to transfer to submarine volcanic systems because electromagnetic waves can barely penetrate the sea surface. We cannot use techniques like INSA, and it's not possible to transfer data streams via wireless communication. And as a result, we as marine geophysicists are most of the time very late to the party. So we arrive at the scenes when the volcanologist onshore already went home. And the main reason for this is that the average time it takes to get a research vessel is 2 to 4 years from proposal to the cruise. And there are significant logistical efforts. So you need to send very heavy and large-scale equipment around the world, and this just takes time and a lot of money. So with the 2025 volcanic crisis, we were in a very lucky situation because already before the crisis, a number of marine geophysical research cruises were scheduled to Santorini. Beginning with the Merian cruise in December 2024, but there was also a cruise by the group of Isobel and one by Christian Höpscher in March and April, and another cruise is already scheduled for December and January. So the seismic crisis from a geophysical point of view occurred at the perfect time between those cruises. And therefore we are lucky and can analyze the data more or less in real time. So the crisis, the tectonic crisis in 2025 initiated in mid-January, and an unforeseen swarm of seismic activity affected Santorini and the area around. And the Greek authority declared state of emergency, and back then more half of Santorini's residents left the island. And during the crisis, it was not clear what is actually happening. And there were fears of an eruption. So the last eruption, as Jonas presented, occurred in 1950. But there were even greater they were even more afraid that a large tectonic earthquake occurs. So the largest earthquake in the last century in Greece actually affected the area and was the 1956 Amorgos earthquake. And at the same time, Santorini is the main tourist hub, and more than 3 million visitors populate the island per year. And so it was very important to find out what is the origin of the seismic unrest. And I was lucky to be part of a larger team who invested the seismic crisis mainly with seismological and geodetic data. So going back to the cruise schedule, so we had this research cruise MSN 132. And during this cruise, we acquired more than 1,200 kilometers of 2D seismic profiles. We acquired 60 square kilometer large 3D seismic cube covering the Amorgos fault. And we collected several days of seafloor image and video footage. And maybe most importantly, we installed 8 ocean bottom seismometers within the crater of Colombo and around it. And these instruments were additionally equipped with pressure and temperature sensors. And finally, we tested the Molar seafloor lander system, with which we were able to acquire seismological data already during the cruise. And back then, we were quite happy that we saw so many signals. What we didn't know back then during the cruise was that we were already uh, in the phase of onset of this seismic crisis. So the run-up phase of the seismic crisis actually began already in July 2024, and it manifested by an increase in seismicity, which became, looking back, obvious already in September. And in addition, there was an uplift of the crater or of the caldera floor. And this was nicely captured by INSA data, which, however, first got recognized with the beginning of the crisis. And as Michele already mentioned, there was a seismic crisis already in 2011, 2012. And this crisis actually, or the processes during the 2025 crisis at the beginning in January, resembled this 2012 inflation event quite nicely. So this is a comparison of both of the ground inflation by INSA, and this is a distribution of seismicity. So the location and frequency of earthquakes were quite comparable, and the people of Santorini felt reminded of the seismic crisis. So in 11 and 12, analysis revealed that magma migrated into Santorini's shallow magma chamber, and there were actually 2 pulses with roughly 12 and 10 million cubic meters of magma. However, at the end of January, things changed significantly. So this is a video of the seismic activity during this phase. And as you see, a large swarm of seismic activity migrated from close to Colombo into the anhydrous block and caused tens of thousands of earthquakes. And at the same time, there were some INSA stations on the island, which showed that the island actually moved towards the area of unrest. And we were very lucky that our British colleagues could retrieve 2 of our instruments, and we could then directly feed the seismological and the pressure data in our analysis. So those 2 instruments were located, one was located directly in the crater of Colombo, and one was on the northern flank of Colombo. And normally, you would not use pressure data from instruments which were just installed, because the systems need to settle and the instrument have a very high drift. So normally you would wait some month until you would use the data. However, in this case, we were lucky that the signal was very strong. So now I repeat the video, and on the right-hand side, you can see the recordings of these 2 pressure sensors. And what you can see here is that the ocean bottom pressure sensor within Colombo, which is this OSP3, subsided by more than 30 centimeters, while the ocean pressure sensor on the northern flank of Santorini subsided by 13 centimeters. So the signal of subsidence was so large that we could actually luckily use them for our analysis. And at the same time, during that period, so from end of January till March, we could also see in this INSA a strong subsidence signal. So having a look at the seismicity in a little bit more detail. So this main phase of activity uh, have can be subdivided in several phases. So the first phase initiated south of Colombo, and back then the seismicity initiated at a depth of about 18 kilometers and was more or less stationary for several days. And then it started to migrate along the Anhydrous Horst and became also slightly shallower. And then there was an interesting effect that the seismicity went actually back in the direction of Santorini and became more and more shallow, uh, up to so as close as 2 or 3 kilometers to the seafloor. Then the seismicity made an excursion further away towards Amorgos before it then migrated back to the area south of Anhydros, where it then with time declined. And after that, so until now, we have seismicity everywhere in the area. However, it's not so strong anymore. And during this phase of very strong unrest, we could see like several surges of seismic activities. They often initiated with a stronger earthquake, and then we had like clusters of very high seismicity, which at the same time when we had a look at the seismic tremors were accompanied by strong seismic tremors. And this surge and tremor activity actually ceased by the 20th of February, when we think the main crisis ended. And we integrated these information, so the seismic information and the deformation information from the INSA data and from the ocean bottom pressure sensors and from some GNSS stations in deformation modeling. And this deformation modeling indicated that in this pre-diking phase, we had a very similar situation compared to 2011, 2012, and about 4 million cubic meters of magma flow into the shallow reservoir of Santorini with a rate of about 0.26 cubic meters per second. During the syndiking phase, the situation changed significantly, and the analysis indicate that we had a dike intrusion with a volume of about 300 million cubic meters, and which initiated at a mid-crustal reservoir. And the peak inflow rates of the diking event was about 200 cubic meters per second, while at the same time we could see this deflation beneath Colombo, so the subsidence, which could be reproduced by a deflation source of about 76 million cubic meters. And this is quite interesting because the ratio between intrusion and deflation helps to constrain the petrology of these intrusions. And a ratio of 4:1 is indicated for rather primitive mafic magma, which was moving back then. And we worked together closely with Emily Hooft and her PhD students. So the velocity models which Michele presented at the end were integrated in our geodynamic model, and the reconstruction of the crisis, which we came up is as follows. So we had a phase of influx of magma into the shallow magma chamber beneath Santorini, which caused increased seismicity, mainly beneath the caldera. And then at some point, this conduit which fed the inflow into Santorini somehow breached and released a dike, which then traveled along this low velocity zone beneath the Anhydros block and created the dikes. And the dike intrusion released a lot of fluids and introduced a lot of stress into the system and caused a lot of secondary seismicity through the reactivation of a complex shallow fault network. And if we now have a look, so we didn't have an eruption, but we think we were pretty close. So the dike intrusion stopped fairly shallow to the seafloor. Recent research cruises did not provide any evidence that we had an eruption. So we were quite lucky. So when we're thinking about eruption scenarios in the area, there are different past eruptions to consider. So the worst case scenario would be an eruption like the 1615 eruption of Colombo, which produced more than 4 cubic kilometers dense rock equivalent, and it caused or it formed a 2,500 meter wide crater. The eruption released noxious gases, which were responsible for more than 70 fatalities and caused a big tsunami, which was 12 to 20 meter high on Santorini and the neighboring island. So this would have been like a worst case scenario if the intrusion would have directly affected Colombo. However, as we know, the intrusion went into the Anhydros block, and parallel to the Anhydros block, we have the Colombo volcanic chain. So I show now a profile covering one of or some of these cones, and they are much smaller. So they have an eruption volume of about 0.1 cubic kilometers, and they're formed in 400 to 500 meters water depth. And we consider these cones to be a limited hazard. So with limited tephra production and actually no tsunami or no explosion. So such an eruption would have meant little harm for the population. However, if a similar eruption would have happened on top of the Anhydros host in shallower water depth, it would have had the potential to create a lot of tephra, very likely influencing marine traffic and air traffic. However, still not far away from this worst case scenarios. So what is next? So we have the cruise in December where we will recover our instruments, and we will redeploy the instruments again, and we will perform many more geophysical experiments. So we will do some magnetotelluric, hydroacoustic surveying, but we will also bring some AUVs to make some high-resolution bathymetric maps. And yeah, so this is what is planned. And yeah, I would like to thank you for your attention. And the last part, so we are currently planning to organize a submarine volcanism workshop next year on Santorini. It's still in the planning, but we aim for October 2026. So everybody who's interested in submarine volcanism or interested in visiting Santorini, yeah, mark the date, and yeah, thank you very much.